Today's topic is DC analysis of MOSFETs. MOSFET DC analysis. In last class, we discussed about basic operation of a MOSFET, and we discussed the circuit simple used for N channel as well as P channel MOSFETs. N-channel MOSFETs, electrons are flowing into the source, so actual current is leaving the source, so arrow is outward. In the case of a P-channel MOSFET, holes are moving into the source, so actual current flow is in the same direction of hole flow, so actual current flows into the source. So this is source, drain, and gate in the case of P-channel. This is drain, source, and gate in the case of an N-channel device. So an outward arrow indicates the channel is N-channel device. Along with, we discussed, these are for enhancement mode, right? Enhancement mode, N and P channels. So if the device is depletion mode, only change is this line will be thicker. That indicates there exists a channel. Rest all are same. Here also channel exists, so this should be thicker. Gate, drain, and source. So this is for depletion mode N. This is for depletion mode P. Right? And as you know, there exists one more terminal called body terminal. Usually it is grounded, and body is always, we are not showing the body terminal. You can mark it as B, body terminal, like this. Dotted line, body terminal, dotted line, body, dotted line, body or substrate. Usually body and sources are connected together. Body and sources are connected together. Right, so it's actually a 4-terminal device, but we are dealing only with 3 terminals: source, drain, and gate. Similarly, we derived ID versus VG characteristics of all 4 categories of the devices. Number 1 indicates a device with the enhancement mode characteristics only because there is no current when gate voltage is 0 in the case of curve number 1. When Vg equal to 0, there is no current, current is 0 for curve number 1. That implies that curve number 1 operates only in enhancement mode, and that Vt is positive implies that is an N-channel device. Similarly, curve number 2, there is no current when gate voltage equal to 0. So that also enhancement mode device, but Vt is negative. That corresponds to a P-channel device. Curve number 3 and 4 operates in both enhancement. Here it is enhancement mode because as gate voltage increases, drain current increases, enhancement mode. The other region here for curve number 4 here, drain current decreases as the magnitude of Vg increases in the negative direction. So we'll call this mode as depletion mode operation. Depletion mode. So your depletion mode device can be either operated in depletion mode or enhancement mode. Current increases with respect to Vg in enhancement. Current decreases with respect to Vg in depletion mode. So curve number 4 corresponding to N-channel depletion mode because current increases further if Vg is positive. That corresponds to an N-channel behavior. So fourth curve is nothing but n-channel depletion mode. Whereas your curve number 3 corresponding to again depletion mode, because in this region drain current decreases as I am increasing my VG, and here drain current increases as I am going negative side of VG axis. So both modes are present. So this area is called a depletion mode operation. Here it is enhancement mode. And the enhancement region is similar to of a curve number 2, that is p-type device. Curve number 2 was p-type. So that belongs to an depletion mode p-channel device. P-channel device. Right? That can be easily remembered if it is a depletion mode device, depletion mode n-channel device. Let us assume depletion mode n-channel. The other device, let us say depletion mode p-channel device, right? P-channel device, depletion mode p. There exists a channel already initially, and you have to apply a negative gate voltage to deplete the channel, right? In the case of p-channel depletion mode, there exists a p-channel. At gate, you have to apply to create a positive carriers. You should apply to deplete the positive carriers. You have to make it n-type. So you should apply a positive gate signal. Here n-channel, to deplete it, you should make it as p. For getting a positive channel, positive carriers in the channel, you should apply a negative voltage at gate. Gate is a silicon dioxide capacitive action. If you are making it positive, you will get a negative carriers here. If you are making it negative at gate, you will get a positive carriers accumulated at the bottom. So to deplete it is n-channel. To deplete it, we have to make it p. So to make it p, I should apply negative. So gate should be negative. To deplete depletion mode p, I should create n-channel or negative charged carriers at the bottom right of my capacitor. So I should apply positive at gate. Right. So threshold voltage in the case of depletion mode n is Vt is less than 0, negative. Threshold voltage in the case of a p-channel depletion mode device, Vt is greater than 0. Whereas in enhancement mode devices, Vt is greater than 0 for n-channel, Vt is less than 0 for p-channel. So depletion mode just opposite. N-channel Vt should be less than 0. P-channel Vt should be greater than 0. So you can expect a one more question based on this. And that we summarized here, negative Vt and positive Vt. Curve number 4, Vt is negative. Curve number 4 is my depletion mode n-channel device. Right? For curve number 3, Vt is positive. 3 is my depletion mode p-channel. Depletion mode p-channel Vt greater than 0. Is that clear? Threshold voltage of depletion as well as enhancement mode devices. Any doubts? Right. So let us have a discussion about drain current in the case of a MOSFET. Drain current versus VDS characteristics. And this discussion is important to identify the condition for saturation and linear or triode mode of operations. Right, so let us take an N-channel case and let us plot the ID versus VDS characteristics. N-channel device, silicon dioxide on top, metal gate, and as usual you have metal connection to source, metal connection contact to drain. Since this is drain, I am connecting a positive to drain terminal. Now I am varying VDS and I am observing the drain current. Drain current IT. Drain current IT. Both currents are same. Drain current entering to the drain is same as the current leaving at source. It's a series path. No other circuitry present in the structure. Third terminal is gate. Gate current is ideally 0. 0 upwards. Right. Suppose gate is biased positive, VG is positive, greater than VT, implies there exist enough electrons or negative carriers in the channel and the channel is continuous and there is a current flow. These electrons present in the channel are attracted by the positive pole. So electrons are flowing into the positive terminal of your battery. So actual current is just opposite direction in this direction. And the circuit obeys Ohm's law. If you are increasing your VDS, naturally the velocity of carriers or electrons will increase. That will increase the rate of flow of electrons, and that will constitute more current. So as per Ohm's law, current varies linearly with VDS. Current varies linearly with VDS. Right? And the condition for existence of the channel is nothing but gate potential to channel potential in each and every point in the channel. The potential difference between gate terminal and each point in the channel should be always greater than VT, so that you have electrons or channel at each and every point inside the device. Let me call it as channel length L. So throughout L, you will have carriers if and only if gate to that point potential is greater than how much? VT, because VT is the minimum voltage required to create the channel, right? And if that condition is satisfied, if you are varying VDS, drain current varies linearly as per Ohm's law. So this region of operation we will call it as linear region or ohmic region, because it's corresponding to the behavior of a resistor. So it's an ohmic region, linear region, or the other name triode region. And that is quite simple. Right. If you are increasing VDS further, the channel potential or potential in the channel also will increase. Why? Because if you are moving from source to drain, source node is a reference node for a drain supply. So if you are moving towards drain, the potential in the channel increases more and more. That is obvious. And the maximum potential is at a drain end here, drain end. Is that okay? And there exists a problem in the channel that the gate potential minus the channel potential at each and every point in the channel is not same now. Gate to channel potential is maximum at source end. Difference between gate to channel potential decreases as we are moving towards drain. And the difference VG minus V channel is least at a drain end. Right? Because the channel potential is maximum at drain end. So the difference between the voltage gate minus channel is least at drain end. Right? So of course, the same channel will not exist at drain end because as we are moving towards drain, the potential difference is less, so the number of charge carriers generated also should be less. So the channel will have a shape like this. Number of carriers generated in the channel is proportional to gate minus channel potential, and that is maximum at source because source is at ground, and that potential decreases if you are going towards drain, and that is minimum. Gate minus channel potential is minimum at drain end because drain potential with respect to ground is maximum at drain end. Right? Suppose a condition exists at which gate potential minus potential at drain end VD is equal to VT or VGD equal to VT implies at drain end we have very small number of electrons, very small number compared to source side. If again you are increasing your VDS further, there exists a situation that makes VG minus VD less than VT, VGD less than VT. So the difference between gate to channel potential at drain end is not at all sufficient to generate the electrons in the channel. So you won't have a channel at drain end. The channel is moving towards source like this. So you have a region here, region that is depleted of the electrons. No electrons in those region. If I am increasing VDS further, this channel will move to source side again, and you'll have another region, let us say Y, in which you don't have any electrons. Right? So the continuity of the channel disappears. And we cannot say that due to discontinuous channel, the current flowing through the channel is equal to 0. Why? Because if you are saying that current equal to 0, then there is no potential drop across the channel. All points will have same potential because current equal to 0, potential difference at source as well as drain and are same. So we'll have an N channel as earlier. That should constitute a current. And due to that current, if VDS is sufficiently large, as we discussed earlier, this channel will move towards source end. And you cannot say that drain current will be equal to 0. And all of you know that to exist a current, there should be a flow of carriers. So the electrons present at this edge should collect by the collector, right? So there exists an electric field in the depletion region because this region is not neutralized. If a region is not neutralized, you will have an electric field E. That electric field drifts the carriers present at this channel edge directly to the drain, right? So there exists a current that is due to the drift of carriers in the electric field created in the depletion region. And we should identify the nature of that electric field. Everybody knows that electric field is nothing but volt upon distance, V by X. And its unit is volts per meter. So denominator X is in meters, centimeters or micrometers. It's a distance. Numerator is a voltage. So as we are increasing VDS voltage, my channel potential increases. VC increases. That is sure. If you are increasing the source voltage, the potential in the channel definitely will increase. And that increase in the potential, channel potential, will decrease the difference between gate to channel potential. Right? Increase in VDS will increase the potential at channel VC, and that VC will decrease the difference between gate to that point channel potential. And hence, the channel moving towards source side. In the other way, if I am marking it as a distance X or channel length L dash, my channel length L dash also will increase as I am increasing my VDS. Due to that, VC increases. Due to that, VGC decreases. Gate to channel potential decreases. Due to that, the depletion region, length of the depletion region, L dash increases. Is that clear? If L dash is increases in the same manner as my V channel, my electric field at each and every point in the channel Let me call it as VC upon L dash. L dash is the distance of the carriers to be traveled. That is a depletion region. VC increases, L also increases. That will give me my electric field constant. That is an ideal approximation. In a practical sense, never voltage to L dash ratio will be a constant. Field will be not constant. For the time being, for drawing the ideal characteristics, let us assume that channel potential and length varies in the same manner so that the ratio VC upon L dash will be a constant. Potential upon distance, that is called electric field. So electric field is constant. VC increases, L also increases, field is constant. Right? So the electric field is constant implies velocity of the carriers also same, because velocity of any carrier is proportional to the electric field. That implies drain current will be constant. If you are varying VDS further, the only difference is that the channel moves towards left, but L dash increases, channel potential also increases, the ratio will be same. So the velocity of the carriers will be same. So current will be same. We will say that the current is getting saturated. And what is the condition for saturation? Gate potential minus channel potential at drain end should be less than or equal to VT. Right? And the starting point of this flatness occurs at which point? It is true if Vg minus Vd is less than Vt, and it starts at a point Vg minus Vd or Vgd equal to a Vt value. Right? So this is the point at which Vg minus Vd less than or equal to Vt, or that single point can be identified by equating to Vt. This region Vg minus Vd less than Vt. Right? Please don't confuse. Vg minus Vd less than Vt. We will derive the other condition also. So the condition was nothing but Vg minus Vt less than or equal to Vt implies your current in the transistor is saturated. That is clear. Onset of saturation is at Vg minus Vd equal to Vt, and that is valid if that is less than Vt. Vg minus Vd. So Vg minus Vt less than Vt. Is that clear? We are bringing our reference terminal, that is source. So Vg is nothing but Vg minus 0, right? Minus Vd is nothing but Vd minus 0, right? Less than or equal to Vt is a constant parameter. And you can see that we assumed source is at a reference, let us say 0 volts. So if I am changing the reference, so Vg minus Vs minus Vd minus Vs less than or equal to a constant Vt. Is that clear? To write it simplicity, for simplicity, let me mark it as this is VGS, Vg minus Vs is VGS minus VDS, Vt minus Vs is VDS less than or equal to Vt for saturation. It's quite simple. So it is nothing but minus VDS less than or equal to VT minus VGS. I am rearranging the terms. Then I am multiplying with a negative sign. So minus will become plus VDS. Less than or equal to will become greater than or equal to. VT will become minus VT. Minus VGS will become positive VGS. So I will write it as minus VGS minus. So this condition I can write it in a better manner. VG minus VD equal to VT condition. That is also right. I can write it as, based on the result, VDS equal to VGS minus VT, right? So this value is equal to VDS, x-axis is VDS, and that value is equal to or greater than VGS minus VT. So I will write it as VGS minus VT. VDS equal to VGS minus VT at this point. And I can write it as VDS is on x-axis. These regions, VDS value should be greater than VGS minus VT. So your MOSFET, N-channel MOSFET is saturated, or condition for saturation is nothing but very simple based on our definition. VDS should be greater than or equal to VGS minus VT. If this is not satisfied, only one condition exists, that is corresponding to linear region. What will be that condition? The other condition. What is the other condition? If this is not satisfied, implies VDS is less than or equal to VGS minus VT. And the point, this single point is called transition point. Transition point. Transition point. Transition point. Right? So if you are asked to identify the transition point of an N-channel MOSFET, you can write it as its VDS value equal to VGS minus VT point, or a point in which your drain current is maximum. And you should not confuse. This curve is plotted for a value of VGS greater than VT as we assumed. And that is a VGS1, one particular value of VGS. So if you are plotting the same curve, you will have a plenty of family of curves based on your different VGS values. If you have a different VGS greater than VGS1, you will have a curve like this. That is VGS2. Please don't confuse. So individual curve for an individual VGS. So if you are increasing your VGS or decreasing your VGS, you will have a family of curves. And that is for a VGS0. VGS 0, 0, 1, and 2. It's obvious that VGS1 is greater than VGS0, VGS2 is greater than VGS1 because you are having large drain current, implies large number of carriers. The more the gate voltage, more number of carriers, and the more current. Right? And this behavior, you see here, input voltage VGS creates an output current or drain current, and that drain current increases as my VGS is increased. My amplifier, all amplifiers will convert what? Input voltage, Vin or VGS, into an output current ID or IC. And if you are passing that current through a large resistor, I will have a V out. Right? So it generates a current, output current proportional to VGS. That is what is observed here. If VGS is increased, I will have a more and more current. Or the MOSFET is performing as an amplifier in which region? Saturation or linear? You please don't confuse with the linear region and amplifier. Linear region here implies your MOSFET output current, drain current increases with which voltage? VDS. Output voltage and output currents are linear in the linear region. See this VDS output voltage on the x-axis, ID output current on y-axis. നിങ്ങൾക്ക് ഓഡിയബിൾ ആണല്ലോ അല്ലെ? എന്തെങ്കിലും ഇഷ്യൂസ് ഉണ്ടോ? ഓക്കെ ആണോ? ഒന്ന് റിപ്ലൈ ചെയ്തേ. ഓഡിയബിൾ ആണല്ലോ അല്ലെ? റൈറ്റ്. ഓക്കെ ഓക്കെ റൈറ്റ്. ചില സമയങ്ങളിൽ നമ്മൾ പറയുന്നത് കേൾക്കുന്നുണ്ടോ സംശയം വരും, അതുകൊണ്ടാണ് ചോദിച്ചിട്ടോ. Right. So MOSFET functions as an amplifier in which region? Not in linear region, saturation region. Why? Because linear region output voltage of the device, that is VDS, and output current are linearly related. That is not the required function for an amplifier. For an amplifier, my input voltage VGS, gate to source voltage, and output current, drain current should be linearly related. That relation can be observed in the active region. You see here, as your VGS increases, you have different curves in which you have different output current ID values. As VGS increases, your output current also increases. So your bipolar junction transistor act as an amplifier in active region or linear region, whereas your MOSFET act as an amplifier in saturation region, not in linear region. Right? And current gets constant or maximizes when VDS reaches VGS minus VT value, or if VDS greater than VGS minus VT value, then also the current is constant. It is independent of the drain to source voltage once it crosses this point. Until that, your current is linearly proportional to VDS, but just after that transition point, your current becomes constant, that is independent of VDS. That depends only on VGS. As VGS increases, your current increases. Right? And condition for saturation is VDS equal to VGS minus VT. You need not remember the other one, this case. If this is false, of course, it will be in linear region. Right? This is for N-channel MOSFET. And you need not by heart the condition for P-channel MOS. Right? Here, one thing you should remember, what about the polarity of VT? In the case of N-channel MOSFET, it's an N-channel enhancement mode device. Enhancement mode N-channel device. What's the polarity of VT threshold voltage? That is positive. You should remember that. Like this. VG versus ID curve. And this was VT. Right? So VT was positive. In your P channel MOSFET, VT is negative, right? ID versus VT, right? And you please see this equation for saturation. What we did in the case of N-channel MOSFET is gate potential minus drain potential less than or equal to VT. So less than or equal to VT for N-channel is no current condition. Similarly, if you are writing for P-channel MOSFET, you should be writing for the region here, current equal to 0 in the case of P region MOSFET, P-type MOSFET. So your VG minus VD should be how much? In this region. All this region, left side, right side of this point is a greater value, right? So VG minus VD should be greater or equal to VT. And you should be careful. This VT is, what is the polarity of VT? Negative threshold voltage in the case of P MOSFET. So if you are writing for a saturation condition of an enhancement mode P-type device, very simple. VG minus VD, initially it was less than or equal to VT because we are concentrating on this region, zero current region. Now zero current region is the other side. So VG minus VD should be greater than this negative VT. VT should be negative. And you will be having only change here, right? Rest everything is same, greater than or equal to VT. And this should be reversed, greater than or equal to, right? So we reached here for saturation, right? So if you are writing it again, up to here only changes to writing the inequality the other way, right? Now it is, let me call it as minus VDS greater than or equal to VT minus VGS. As we did earlier, I'm multiplying with a negative. So VDS less than or equal to VGS will become positive minus VT. And that is the condition for AP channel device. So I will write it here. For an N-channel device, my condition was VDS greater than or equal to VGS minus VT. For my P-channel device, now I got a different condition that VDS less than or equal to VGS minus VT. VDS less than or equal to VGS minus VT for saturation. For saturation, you have to remember that only. The other way it is in linear mode. And the one thing you should remember always is this VT is what? Positive. What about this VT? Negative. That's it. Okay. Is that clear? Two equations. And fundamental equation was this one. VG minus VD in the case of N channel less or equal. VG minus VD greater or equal in the case of a P channel device based on these two fundamental curves. Is that clear? Any doubts? These are fundamental things to be identified before getting into the problems, DC problems of MOSFET. I hope this is clear. Any doubts? Because clarifying your doubts after some time will take much more time. That's why I'm asking. Any doubts? I hope it is clear. Anybody without understanding the condition for saturation in the case of N channel, P channel. Let us discuss only enhancement mode P, enhancement mode N. Right, I think it's clear, right? And your different textbooks, you will see different expressions corresponding to this that you can also write, no issues. If you are multiplying this equation with a negative sign, or if you are writing it as V ds greater than or equal to VGS minus magnitude of VT, you can write it as no issues, because N channel VT is always positive, magnitude of VT is also positive. Similarly, you can write it as VDS less than or equal to VGS plus magnitude of VT, no issues. Because this is negative, and negative will become positive, so plus a term, so you can write a plus magnitude of that. That is also true. Right? If you are multiplying with the negative sign, VSD less than or equal to VST plus VT. That is also true. If you are multiplying with a negative sign, VST greater than or equal to VST plus VT. You should remember this will be negative. So many ways you can write, but you need not go for all these expressions. A simple thing you can remember is these two equations, and that too logically done by hand. Only remember about these characteristics in your mind always, that output characteristics, this one. And please ensure that this you understood it as VDS equal to VGS minus VT point in the case of N channel device. Greater than that is a saturation condition. Condition for saturation. That you can easily remember. VDS greater than or equal to VGS minus VT, and you know that VT is positive. And the other inequality you should write for P channel, VDS less than or equal to VGS minus VT, and you should remember that VT is negative. And the same thing can be derived yourself based on the logic we have discussed right now. That's it. Okay, is that okay? Right. So that's about condition for saturation and linear. And to analyze the MOSFET DC circuit, we should identify the drain current in your circuit. So we should understand the expression for drain current to be used in the circuits. So as we discussed, current is always proportional to the flow of carriers, right? Flow of electrons in the case of N-channel device. So drain current in the case of N-channel device is proportional to mobility of an electron. That is why, because the velocity of an electron is related to constant to the electric field, and that constant is called mobility or mu. So as mu increases, velocity also increases, we'll have more current. So ID is proportional to velocity. ID is proportional to the width of the device. That is obvious. If you have more width, you will have more number of carriers. Directly proportional to width. And you have an oxide layer between gate and your channel. The created N layer, we will call it as inversion layer or N channel, or number of electrons accumulated at the bottom plate of your capacitor. This is SiO2. So it will have a particular value of capacitance, we'll call it as oxide capacitance, Cox. And from the fundamental equation, total charge in a capacitor equal to C times V. So total charge in this case equal to, this is oxide capacitance Cox, multiplied by voltage applied at gate Vg. The more the Cox, you will have more charges. So you'll have a more drain current. So directly proportional to Cox. That is also quite simple. What about the length of the channel and proportionality of drain current? Length of the channel. Resistance is rho L by A. If the distance to be covered by the carriers is more, of course it will have more resistance. So ID is inversely proportional to L. Right? And what about VGS? If you have more VGS or more VG, you will have more drain current and more charge carriers. So ID is proportional to VG also. To include the reference, we'll mark it as VG, gate to source voltage. And as we discussed in the output characteristics, see here, current is increasing with a VDS. So I am going to write in the linear region. See, current is increasing linearly with a VDS. So in your linear region, current is proportional to your drain to source voltage also. So I am writing for linear region. So in linear region, ID equal to mu n directly proportional to Cox directly proportional to W width of the device inversely proportional to the length by L proportional to VGS, but the minimum VGS required is threshold voltage VT. So I should write VGS minus VT because at VGS equal to VT, the current should be 0. So there should be a term VGS minus VT instead of VGS. Right? If VGS is less than VT, this expression is not valid. The device should be on to have a current. To on the device, VGS should be greater than VT. So I should replace VGS with a VGS minus VT. Multiplied by the last dependency is the linear region, linearly depends on VDS. You should be careful. VGS is constant, VT is constant. These all are constant. In our graph, in our output characteristics, one curve is for one particular VGS, right? So all parameters here are constants except VDS. So ID equal to constant times VDS, ID equal to K times X because VDS is on the X axis. So that is the equation for linear region. Drain current in linear region. Right. Current increases linearly, then it should become flat. At a value VDS equals VGS minus VT. Right? So now we are here. We derive the linear equation of current, linearly proportional to VGS. Because for a given curve, VGS is constant. Right? So in your saturation region, it's linearly increasing. Slope is positive here. Now suddenly slope becomes how much? 0. So that kind of behavior happens when mu and C of W by L as earlier, VGS minus VT as earlier, VDS as earlier, no change. Then positive slope should become 0. You should have a negative term with respect to x-axis, that is VDS. So that a positive slope at VDS equal to VGS minus VT will become flat. And to get a linear to non-linear, flatness is a non-linear. To get a linear to non-linear transformation, you should have at least a second order. So that term is VDS square upon 2. We have proof for this, but we are not discussing that proof right now. So it should be negative and should be second order. So we are taking power 2. There should be a constant along with that, k VDS square, k equal to 1 by 2. So VDS square by 2 in saturation. And the current continues as same current at VDS equal to VGS minus VT, no change. So if you are replacing your VDS with the VGS minus VT in your linear equation, you will have a saturation condition, because here, all other regions greater than VGS minus VT range, current is constant. That current is equal to a value with VDS equal to VGS minus VT. So this VGS minus VT will be squared. Then VGS minus VT, the whole square upon 2, you will have mu n C ox W by, that 2 will come here to L, and VGS minus VT, the all squared. Constant into VGS minus VT all square minus VGS minus VT all square by 2. So 1 minus 1 by 2 is 1 by 2. So 2 will come here, mu and C ox W by 2L into VGS minus VT, the whole square. And this is the equation for saturation. And this is the equation for linear region. Very low values of VDS. And this equation is common for both, right? It is clear that if VDS is very small, VDS square will be still smaller than VDS. So this term can be neglected in the linear region. You will get the old equation mu and C ox W by L into VGS minus VT multiplied by VDS. That is valid. ID equal to mu n C ox W by L into VGS minus VT times VDS. This expression we are not using by solving the problems. 99 questions correspond to saturation. So this is valid for a very small VDS, especially in the origin, close to origin. And the second equation is valid for a region up to here, all linear regions. So ID equals mu n C ox W by L into VGS minus VT minus into VDS minus VDS square by 2 is corresponding to entire linear region. And the last equation is well known, saturation equation, mu n C ox ID equals mu n C ox W by 2L, mu n C ox W by 2L, C ox W by 2L into VGS minus VT, the whole square is for saturation. So you need not remember this while doing the problems. You need not remember this while doing the problems. We'll go with only one equation. And it is clear that no X term, no VDS term, no VDS term in the expression. That implies it is a flat curve in the saturation because it never depends on VDS value. It depends on only a VGS minus VT squared multiplied by mu and C of W by 2. And these two equations we are not going to use anywhere. But if you're asked to identify what will be the equation in the neighborhood of origin, here you can easily say that is linearly proportional to VDS, and this is the first equation. And what is the equation of entire linear region including this point? You can say that there should be a nonlinear term to make it linear to nonlinear transition. So you can say that it is minus VD squared by 2. And VDS square is very, very small. You can neglect it. You will end up with the first equation in the neighborhood of origin. And this equation we are going to use everywhere while solving the problems. And that is independent of VDS, VGS minus VT. And this is valid if and only if what is the condition for saturation? VDS greater than or equal to VGS minus VT. And the transistor should be in on state. So VGS should be greater than VT. ഒരു കാര്യം നിങ്ങൾ ശ്രദ്ധിക്കുക, ട്രാൻസിസ്റ്റർ ഓൺ ആണെങ്കിൽ മാത്രമേ ഉള്ളൂ ഏത് റീജിയൻസ്, രണ്ട് റീജിയൻസും ലീനിയർ ഓർ സാച്ചുറേഷൻ. ഇഫ് ട്രാൻസിസ്റ്റർ is not on, if VGS is less than VT, transistor is off, drain current is always equal to 0. So you should check whether the transistor is on. If it is on, two possibilities, either linear or saturation. 99% all transistors will be in saturation. Right? Is that clear? Anything extra to be discussed? And we took 1 hour to complete the fundamentals of MOSFET current equations. We'll get into the problems. Anything, any doubts, any problems, any issues? Only one equation and one condition you should remember. Condition for saturation, VGS minus VT here. VGS greater than VGS minus VT. And equation for saturation. Mu and C of W by 2L into VGS minus VT. Right. Let us get into the problems. Problems are quite simple once you are comfortable with these two conditions, drain current with the condition for saturation. It's very simple. Let us have one condition. Identify the mode of operation of the N-channel MOSFET shown below. Identify the mode of operation of the transistor shown below. First option A, saturation. B, linear. Third option, off state. Fourth option, it depends on Vx. Answers very simple. And you should know the terminals based on the simple. Yes, Balu says saturation. Bindya says saturation. Right. What about others? Yes. Okay. Okay. Ambali says A. Surunda says A. All right. Any other answers? Right. What is VDS? VD minus VS is my VDS. That should be greater than, for saturation I am writing. Right. That should be greater than VG minus VS is, right. Simi says saturation, right. Very good. Minus VT. VT is given as positive 1. It's an N channel MOSFET. Positive 1. And if you're adding VS on both sides, you can cancel that VS. So VD greater than or equal to VG minus 1. VS will cancel from both sides. And this is my VS. VS equal to VX. And it turns out to be, it is independent of Vx, right? Vx. And drain voltage in the circuit is equal to 5, that's greater than. And gate is tied to the drain, so Vg equal to Vd, that also equal to 5 minus 1. Of course, all of you knows that 5 is greater than 4. And this equation is satisfied. So it is independent of Vx. This was by source voltage. But you should identify that if Vx equal to 5, what will be your answer? If Vx equal to 5, your VGS is nothing but Vg minus Vs. So VGS equal to, Vg is nothing but connected to 5 volts. So 5 minus, what is Vs? Source is, this is source, voltage at source is nothing but Vx, that is 5. 5 minus 5 equal to 0. So my VGS is equal to actually 5 minus Vx in general, right? So if Vx is less than or equal to 4, your transistor will turn on. Why? Threshold voltage is given as 1 volt. So to turn on the transistor, VGS should be always greater than VT. Here it is 1 volts. And VGS is 5 minus Vx. So that implies 5 minus Vx is greater than 1 volt always. So minus Vx greater than minus 4. Vx should be less than 4 volts. So if Vx is given, in the available options, you cannot go for saturation condition. It depends actually on Vx. If Vx is less than 4, transistor is on, then it is in saturation, no doubt. If Vx is greater than 4, then it is in off state, then option C. So actually that depends on Vx. If Vx is less than 4 is given, then as you said, you can go for saturation, no issues. If source is grounded or Vx equal to 0, then also your option was correct. You can go for saturation. If it is a general variable Vx, that will not depend on your saturation or linear condition, that is independent of Vx, that is true. But Vx should be such that, or source voltage is such that, that should turn on the transistor, right? right? If it is +1, definitely it will turn on the transistor VGS is 4 greater than 1 volt VT. Then your answer is saturation. Otherwise, if Vx is a general variable, you can go for it depends on Vx, right? Okay. So you should be careful with respect to the value of source potential, right? Let us see the similar condition for an p-channel device like this p-channel device. Here +5 volts, this is grounded, and Vt equal to -1 volt. What's your answer? Saturation, linear, cutoff, none of the 4 options. Right, condition for PMOS. Always remember saturation mode. Yes, Balu says saturation, right? That will be correct, right? Condition for saturation. What was the condition for saturation of NMOS? Sorry, PMOS. PMOS was saturation VDS less than VGS minus VT, right? VDS less than VGS minus VT, right? VDS less than or equal to VGS minus VT. VT is -1. So VDS is nothing but VD minus VS less than or equal to VG minus VS minus VT is negative. So minus of -1. So VS can be cancelled from both sides. So VD less than or equal to VG plus 1. VD and VG are same. This is VG, this is VD. And both are grounded. So VD is less than or equal to VD plus 1, or VD equal to VG. VG is always less than or equal to VG plus 1. That equation is satisfied. So this is in saturation. The transistor will be on definitely. Why? Its VGS is nothing but VG minus VS. VG is nothing but 0 here. So 0 minus Vs is 5. So Vgs is nothing but -5. And that is less than your -1. You're operating at -5. So definitely it will be in on state. Right? That was very simple. Is that clear? Anybody, any doubts? Any issues? Okay, let us get into the other problem. That also very simple. Logically, you can solve it. Supply voltage is positive 3 volts. RD is unknown. Source is grounded. Gate, you directly given positive 1.4 volts. Applied. Parameters are given mu n C ox W by L 2 milliampere per volt square. Mu n C ox W by L equal to 2 milliampere per volt square. Mu n C ox W by choice of L equal to 1 milliampere upon volt square. You can go for always saturation. Okay. And the question is not complete, right? Given. Vt is also given. Vt equal to 0.4 volts. Question, find the value of Rd. Find Rd at transition point. Transition point. Transition, Transition. Transition point. Find the value of RD at transition point. Mu1 Cox W by 2L value is given 1 milliampere per volt square. You should be careful about the unit of that constant. That constant is equal to ID divided by VGS minus VT the whole squared. VGS minus VT in volts, so volt square. ID is in ampere or milliamperes. So unit of mu1 Cox W by L will be milliampere or ampere per volt square. VT is 0.4 volts. RD is unknown. Supply voltage is 3 volts positive. Gate is connected to 1.4 volts. Find RD at transition point. Always you can assume the transistor is in saturation, because that's a simple expression. Only one term is there, VGS minus VT the whole square. Always assume transistor is in saturation. And you should understand what is the property of transition point. What is the condition at transition point? At this point, we have so many conditions. One important condition is 2K, right? Okay, answer is 2K. Let us see that. Okay, at transition point, this voltage VDS should be how much? VGS minus VT. That we know. And the current is maximum for a given VGS, right? And one more thing, at this point, both linear as well as saturation equation of drain current is valid. And we are dealing with only saturation equation because that is quite simple than your linear mode equation. Why? Because in your linear mode equation, you will have a square term, 2 terms. And saturation mode equation is quite simple, only a square term VGS minus VT, that will be constant always, most of the time. Right. So what is VGS? And I should identify VDS, and that I should equal to which value? My VDS should be equal to VGS minus VT, right? There will be a drain current flowing through the circuit. Then depends on VGS minus VT difference squared multiplied by the constant. All constants are given to you. That current creates a drop across RD, IDRD, right? ID multiplied by RD. And the, right, 2K, okay, right, very good. And VDS is nothing but, what is VDS? Total voltage is 3 minus drop across RD is equal to your VDS, right? So 3 volts minus ID multiplied by RD will give your VDS. And that should be equal to VGS. How much is your VGS? This is your VGS. VG minus VS is VGS. VS is grounded 0 volts. So VG minus VS is 1.4 given minus 0. Right, very good. 1.4 minus 0.4 is your given VT, right? So, right, very good. 3 minus ID multiplied by RD will give you 1 volts, right? At transition point, this equation to be valid, and you should find ID first to know the condition on your RD. How much is ID? ID, direct substitution, mu1 Cox W by 2L. Mu1 Cox W by 2L is given as 1 milliampere per volt square, right? Multiplied by VGS minus VT is how much? 1 volt only, 1 squared. So ID will be equal to 1 milliampere, right? Mu1 Cox W by 2L equal to 1 milli minus VGS minus VT is 1. So ID equal to how much? 1 milliampere, right? So 3 minus 1 equal to ID. ID is 1 milli. If RD is in kilo ohms, 2 equal to ID in milliamps multiplied by RD in K. Milli K will cancel each other. So RD should be how much? 2 kilo ohm. So RD value should be 2 kilo ohm. Right, very good. RD equal to 2 kilo ohm. So the observation is, if you are varying your drain resistance, you can control the mode of operation. Remember, the drain current is proportional to VGS minus VT, that is independent of RD in this circuit. So ID is fixed based on VGS minus VT all square times constant. And if you are increasing RD, ID-RD drop increases, 3 minus ID-RD drop decreases, or VDS decreases. So if you are increasing RD, VDS decreases. If VDS decreases, it is moving towards linear region, right? If you are decreasing RD, VDS will increase, that will move to saturation region. So at transition point, we found that it will be 2 kilo ohm. If RD is greater than 2K, it will move to which mode? RD greater than 2K, it will move to saturation or linear. RD equal to 2K at transition point. If RD is greater than 2K, VDS will decrease, it will move to linear region. If RD is less than 2K, VDS will increase because current ID is constant, right? RD less than 2K, VDS increase, that will move to saturation. So in your last problem, if you are inserting an RD greater than 2K, that will bring your transistor into linear region, right? Linear region. If RD is less than 2K, and that will ensure your mode of operation in saturation. Is that clear? If you are asked to find out what is the maximum value of RD such that the transistor remains in saturation, how much is the answer? What is the maximum value of RD in the same problem? What is the maximum value of RD such that the transistor remains in saturation? What is the answer? Anybody? Maximum value of RD such that transistor remains in saturation. Quickly. Last problem. Transition point, you got it as 2K. Right, Donia says 2K, right, very good, Surendra, very good. Right, maximum value is 2K because if you are increasing beyond that, it will go to linear mode. So question is such that the transistor is in saturation. So for saturation should be less than or equal to 2K. Less than or equal to 2K. Right, so based on that, we will have questions, and that is quite simple. Don't afraid of seeing the MOSFET circuit. It's quite simple, simpler than your transistor circuit. Let us have another interesting problem that based on region of operation of an P-channel MOSFET. P-channel MOSFET. Let us have a circuit. Right. P-channel MOSFET is shown. P-channel. Right. P-channel MOSFET. Supply voltage positive, VDD instead of VCC MOSFET. 1 We'll mark VDD or VSS, source is connected, VSS equals plus 2.5 volts, positive 2.5 volts. Drain voltage is constant with respect to ground, 1 volts. Input is, as earlier, Vx. VT, P channel MOSFET it is, so VT should be negative minus 0.5 volts. Question is quite simple. Identify the range of Vx, such that the transistor remains in saturation. Of course, you will have 4 options. Let me write the options also. You can start your solution. You can start solving the problem. Options I will write. So options are, let us see, saturation. Let us say Vx is less than or equal to 0.5, less than or equal to 2. That is one option. Vx less than 0, less than or equal to 0, second option. Vx greater than 2, third option. Two less than or equal to Vx less than or equal to 2.5. Fourth option. All options are given. First option is 0.5 to 2 volts saturation. Second option Vx less than 0 saturation. Third option Vx greater than 2 saturation. Fourth option Vx between 2 to 2.5 saturation. Only one equation you have to apply this. Very simple. VDS N channel MOSFET less than or equal to VGS minus VT for saturation PMOS, right? 1 point VT should be negative. That you should do it carefully. So VD minus VS less than or equal to VG minus VS plus 0.5. VD is 1 volt. VS will get cancelled from both sides. Right, option A. Donia says option A. Very good. Right, again option A. Salihat option A. Right, VD is 1 less than VG values. Right, option A. Archana says option, not that option A. Right, so that A. Right, very good, very good. VD less than or equal to, right, VG minus VS. VG is nothing but Vx. Vs can be cancelled from both sides. Vs plus 0.5. So Vx should be greater than or equal to 0.5 for saturation. Right? Saturation. Right. So Vx should be greater than 0.5 for saturation. But I have option A that satisfies that. Vx greater than 0.5 and Vx greater than 2, right? Vx is between 2 and 2.5. Right. So what is the condition? If you are plotting that Vx, if Vx exceeds 2 volts, let us say 2 volts. If Vx is greater than 2 volts, its VGS should be always less than, it's a p-channel device. So VGS should be less than how much? Minus 0.5, less than or equal to minus 0.5 always, right? So if 2 VG exceeds 2 volts, so VG minus VS, VG is 2, VS is 2.5, so VGS will become minus 0.5. If again increasing from 2 volts, the transistor will go to off state. So beyond this, it is in off state. Is that clear? VGS should be negative less than 0.5 for a given p-channel MOSFET. If VG is increasing beyond 2 volts, VGS will become greater than minus 0.5 volts. So that ensures an off state. And for saturation, your condition Vx should be greater than 0.5. So Vx should be greater than 0.5 up to 2 volts. It will be in saturation because up to 2 it is in on state. Greater than 0.5 is the required condition for saturation. So 0.5 to 2 it is in saturation. That's why you're getting upper limit here 0.5 to 2. Upper limit is 2. So option A is the right choice as you said. And what about a point less than positive 0.5? Vx less than 0.5 implies it is in a linear region, right? So if you are decreasing your Vx, the transistor always in on state. So on state with this condition not satisfied, so that is in which mode? Linear mode. Up to minus infinity, it is in linear mode. It will not change. So maximum value of Vx that ensures a saturation is 2 volts. Minimum value of Vx that ensures a saturation is 0.5 volts. Maximum value of Vx that ensures a linear operation is plus 0.5 volts. Minimum value of Vx that ensures a linear mode of operation is up to minus infinity, no restrictions. Maximum value of Vx that ensures on state of your p-channel, given p-channel MOSFET is 2 volts, right? So we are relying on a simple equation along with the condition for on state. Then you can have any number of questions based on that. So last problem, option A is the right choice. Any doubts with respect to your p-channel MOSFET? Any issues, any doubts? P-channel MOSFET? Right. P-channel MOSFET conditions are rarely asked. Most of the questions are from N-channel MOSFET. Anyway, we discussed P-channel also, right? Let us have one more interesting problem based on an N-channel MOSFET that uses one resistor, one supply voltage, and one MOSFET, right? All right, let us have another circuit. N-channel MOSFET. Drain and gate are connected together. Source is grounded. Supply voltage is plus 5 volts. RD is given as 1.5 volts. Sorry, 1.5 kilograms. Very simple. VT is the parameter given as 1 volts, positive, N-channel MOSFET. VT should be positive. Mu n C ox, constant mu n C ox given as 1 milliampere per volt square constant. And width length of the device L1 is given as 1 micrometer. 1 micrometer. You are asked to find W1, width of the device. Also given that the current, drain current flowing through the transistor is 2 milliamperes. ID equal to 2 milliamperes. It's a very simple problem. Identify the mode of operation, apply the saturation condition equation, solve for W1. Which mode it is operating? Drain and gate are shorted together. In any transistor, if drain and gate terminals are shorted together, without any doubt, you can simply say that the transistor is operating in saturation, because VDS will be always greater than VGS minus VT. VD always greater than VG equal to VD, so VD minus VT. So this is in saturation. And drain current is given to you. You can substitute and find the value of L is W1 easily. So 2 milliampere current flowing through this. Mu n Cox W by 2L. Please don't miss that 2. 2L was our equation, multiplied by VGS minus VT the whole squared. So don't worry about VGS. VGS is same as your which voltage? VDS, right? Because gate and drain are shorted together. VDS equal to VGS. How much it is? VDS is nothing but, as we discussed earlier, total voltage is 5 minus drop across RD. What is the drop across RD? RD is 1.5K. ID is 2 milliampere. 2 into 1.5 equal to 3 volts. 5 minus 3, 2 volts. So VDS is equal to 5 minus 1.5 into 2. 1.5 into 2 is 3. 5 minus 3 is 2. VDS is equal to 2. That's equal to VGS. And constant is given mu n Cox 1. So 1 by 2. W1 is to be identified, divided by L1, right? Multiplied by VGS minus VT. VGS is 2 minus VT is 1. Right, address is 1 micrometer. Right, let us see that. VGS minus VT. VGS is 2, VT is 1, so 1 squared. And this parameter is 1 milliamps per volt square, so that milli and milli will get cancelled from both sides. So 2 milliamps here, this is in milliamps per volt square. This milli will cancel each other. VGS minus VT whole square is in whole square. This whole square will cancel each other. Right. So 4 equal to W1 by, right. Two answers, 1 micro and 4 micro. Let us see that. W1 by L1. L1 is 1. Right. L1 is 1 micro. Right. So W1 in micro. Right. Very good. L1 is 1 micro. So that should return a 4. So W1 should be in 4 micro. Right. 4 micro. Right. Very good. Right. In the same problem, if you are asked to find out what is the maximum possible value of ID max, such that the transistor is operating in saturation, what will be your answer? ID max corresponding to saturation mode. As we discussed earlier, ID increases, IDRD increases, VDS decreases. And the least value of VDS is nothing but how much? VGS minus VT. In this particular example, VGS is nothing but 5 minus ID multiplied by ID max multiplied by RD minus 1. That's equal to your VDS. And you should solve for VGS, which is equal to VGS. Then you have to substitute for VGS here. Then RD value is known to us. You can directly evaluate ID max. So this is not simple. You should identify VGS in terms of ID max. Then you have to substitute it. Then find the value of ID max. Because VGS is a function of ID max. It's not a constant. Right? You can try this as a homework. That's a little bit length. Any answers? Maximum value of ID? And you can take a W value equal to 4 micro. That should be given. 4 micrometer. Based on that, you can solve for maximum possible value of ID. Right. You can do it as an homework. Right. And let us get into another circuit that we will feel that it's a complex circuit, but that is actually simple. Let us see that. Two transistors, both are operating in saturation because both gate and drain are connected together. Right. Supply voltage is plus 5 volts. Drain current is 1 milliampere. RD equal to 1.5 kilo ohm. Both drain voltages are given to you. That makes it simple. 3.5 volts here, 1.5 volts here. And both case VT are equal to plus 1. VT equal to 1, upper 1, lower 1 also, VT equal to 1. And both case L1 equal to 1 micrometer as earlier. Here also L2 is same as 1 micrometer. Both transistors channel length L1 and L2 are same. That's equal to 1 micrometers. Then the parameter is also given mu n C ox equal to 1 milliampere per volt square as earlier. 1 milliampere per volt square. Identify W2 upon W1 ratio. So lower one is transistor M2, upper one is transistor M1. W2 by W1. 4 options. 1 by 2, 2, 4, 8. Both transistors are in saturation because both cases drain and gate are connected together. And all of you know that there is no gate current for an ideal MOSFET. So the 1 milliampere current flowing through the upper resistor, 1.5 kilo ohm resistor, will flow as a drain current of upper transistor. Thus, that will come out through the source, 1 milliamps. Again, no branch current, 0 amperes to the gate. Same 1 milliamps flows as a drain current of lower one that leaves here. Right, Archana says 4. Right, let us see that. So the point is both the transistors carries equal current. Both are in saturation. So both transistors we should have a 1 milliampere current. Both are operating in saturation. Mu and C ox multiplied by W by L of 1 by 2 VGS minus VT is 1 whole square. This is for transistor 1. For both transistors, your parameter mu and C ox is 1 milliampere per whole square. So VGS1 upper transistor. What is VGS1 of upper transistor? Right, Adira says C. Right, very good. VGS is gate to source voltage. Gate to source voltage, that is same as drain to source voltage because gate and drain are shorted. Source with respect to ground is 1.5 given. Source of upper transistor is 1.5 with respect to ground. Drain of upper transistor is 3.5 with respect to ground. So difference between drain voltage to source voltage of upper transistor is VDS is 3.5 minus 1.5, that is 2 volts. Right, 2 volts. Again, 1 milliampere for the lower transistor. Same thing, mu and C ox W by L of 2 divided by 2 VGS2. What is VGS2? Is same as your VDS2. VD is 1.5 with respect to source. Source is at ground. So VGS2 minus VT is 1, both cases all squared. So this is nothing but 1.5. Right, so if you are taking the ratio, let me call it as equation number 2, equation number 1. Taking the ratio 2 by 1, left hand side you will get a 1 million, 1 milli, 2 by 1 equals 2 will get cancelled, mu and C ox will get cancelled. 2 by 1 will give you W by L of 2 upon W by L of 1 multiplied by 1.5 minus 1 is 0.5. So 1 by 2 all square on the numerator divided by 2 minus 1, here it is 1 squared. And L values are same, both M1 and M2. Right? So we'll get 1 equals, L will cancel each other, W by W of 2 by W of 1, L will cancel each other, equal, multiplied by 1 by 2 whole square is 1 by 4. That implies your W2 upon W1 ratio, 4 will go to left hand side, equals 4. As you said, it's 4. And it is obvious that both transistors are carrying same current, and that current is proportional to VGS1 minus VGS1 minus 1 whole square, VGS2 minus 1 whole square. But VGS1 of upper transistor is 2 volts, that is greater than VGS2 of lower transistor. So to ensure same current, a transistor with a lower VGS should have a larger W in this example. So W of 2 should be larger than W of 1. So W2 by W1 ratio should be greater than 1. So first option is anyway wrong. And that ratio is proportional to ratio of VGS1 minus VT the whole square divided by VGS2 minus VT the whole square. So we'll get it as 1 square divided by 1 square divided by 1 by 2 the whole square, that will give you 4. So same transistors operating in saturation, same drain current ensures a larger W for a transistor with lower VGS. Is that clear? Any doubts? So your answer is third option, 4. We'll wind up the session by discussing one more interesting problem based on what we have discussed right now. Then we will wind up. Similar to last case, you have 2 transistors, N channel. Both are operating in saturation. Grounded. Both are identical. Both VTs are same. Plus 1, let us say, and plus 1 volts. Both are same. Both mu n C ox W by L of 1 is equal to mu n C ox W by L of 2. They're all parameters. W by L, mu n C ox, everything is same. Supply voltage is plus, let us say, plus 6 volts. 6 volts. This is marked as Vx. You have to identify the value of Vx. Both transistors are identical. Their VTs are same. Their mu and Cox W by L ratios are same. Total supply voltage is 6 volts. Identify the value of Vx. Options are 1 volt, 2 volt, 3 volt and 4 volts. 1, 2, 3, 4 are options. The point here is both are in series, both of them carries equal drain currents and both are identical transistors. All parameters are exactly same. Right. Dunia says option 3. What about others? Right. Suranda says 3. What about others? Archana 3. Right. What about others? ആൻസർ സ്ഥിരമായിട്ട് പറയുന്ന ആളുകൾ മാത്രമേ പറയുന്നുള്ളൂ, ബാക്കിയുള്ളവര് ചെയ്തിട്ട് പറയാതിരിക്കുന്നതാണോ? ചെയ്യാൻ ബുദ്ധിമുട്ടുണ്ടോ? ബാക്കിയുള്ളവരോട് പറഞ്ഞ ആൻസേഴ്സ്. രണ്ട് ട്രാൻസിസ്റ്ററിനും സെയിം ഡ്രെയിൻ കറന്റ് ആണെങ്കിൽ, രണ്ടും സാച്ചുറേഷനിലാണെങ്കിൽ നമ്മുടെ എക്സ്പ്രഷൻ നമുക്കറിയാം. ഐ ഡി ഈക്വൽ ടു mu n C ox W by 2L into VGS minus VT. ഇത് സെയിം ആണ്. ഐ ഡി ഈ പാരാമീറ്റർ എന്താണ്? സെയിം ആണ്. റൈറ്റ്. ലക്ഷ്മി says 3 volt. റൈറ്റ്. ഓക്കെ. വി ടി എന്താണ്? സെയിം ആണ്. അപ്പൊ രണ്ട് ട്രാൻസിസ്റ്ററിന്റെ ഇക്വേഷൻ ID1 and ID2, right? C ox W by 2L into VGS2, this is VGS1 minus VT. All VTs are same, all square. രണ്ടും എന്താവണം? സെയിം ആവണം അല്ലെ? അപ്പം ഇത് കോൺസ്റ്റന്റ് ആണ്, ഇതും കോൺസ്റ്റന്റ് ആണ്, രണ്ടിനും സെയിം തന്നെയാണ്. രണ്ട് കറണ്ടും എന്താണ്? സെയിം തന്നെയാണെങ്കിൽ എന്ത് സെയിം ആയേ പറ്റുള്ളൂ? ഈ സ്ക്വയർ ടേമും സെയിം ആയേ പറ്റുള്ളൂ അല്ലെ? സ്ക്വയർ ടേമിനകത്ത് എന്താ ഉള്ളത്? VGS2 മൈനസ് VT ആണ്. VT എന്താണ്? സെയിം ആണ് നമ്മൾ പറഞ്ഞു, സെയിം ആണ് അല്ലെ? അപ്പൊ VGS1ഉം VGS2 എന്തായിരിക്കണം? സെയിം ആയിരിക്കണം. സോ VGS1 should be equal to how much? VGS2. സിമ്പിൾ ആണ്. റൈറ്റ്. VGS1ഉം VGS2ഉം എങ്ങനെ അപ്പിയർ ചെയ്യണത്? ഇങ്ങനെയാണ് നമ്മുടെ കണക്ഷൻ അല്ലെ? ഇവിടെ 6 വോൾട്ട് ആണ് കൊടുക്കുന്നത്, ഗേറ്റ് ഇവിടെ കണക്ട് ചെയ്യുന്നു. റൈറ്റ്. And second transistor is connected like this, this. This is grounded. Right. So this is VGS of 2. This is MOSFET 2. This is MOSFET 1. This is VGS1. ശരിയല്ലേ? അപ്പൊ നിങ്ങൾ നോക്കിയേ, ഈ സർക്യൂട്ടിൽ ഇവിടെ 6 ആണ്, പോസിറ്റീവ് 6 ആണ് അല്ലെ? പിന്നെ ഇത് പ്ലസ് മൈനസ് VGS1 ആണ്, ശരിയല്ലേ? ഓക്കെ, നിങ്ങൾ ഗേറ്റും ഡ്രെയിനും ഷോർട്ടഡ് ആണ്. സോ VDS is same as your VGS. So VGS1 is same as your VDS1 അല്ലെ? സെക്കൻഡ് ആൻസർ നിങ്ങൾ നോക്കിയ ഗേറ്റും ഡ്രെയിനും ഷോർട്ടഡ് ആണ്. സോ VGS2 is same as your VDS2, ശരിയല്ലേ? VGS1ഉം അല്ലെങ്കിൽ VDS1ഉം പ്ലസ് മൈനസ് അനദർ VDS2ഉം കൂടെ ആഡ് ചെയ്യുമ്പോൾ എന്ത് കിട്ടണം? നമുക്ക് 6 volts കിട്ടണം അല്ലെ? സോ VDS1 plus VDS2 equal to 6. And we identified that both VGS1 and VGS2 are same. That implies VGS1 plus VGS2 equal to 6. Both are same, implies VGS1 equal to VGS2. And this is 3 volts. This VGS is also 3 volts. And what is VX? VX is same as your VGS. So that should be equal to 3 volts. Right. So without doing anything, by looking into the circuit directly, you can go for 3 volts. Don't afraid if you are seeing more number of transistors. Is that clear? Any doubts? Let us wind up today's